All right, so now we've seen what L'Hopital's rule is. Right, let's see how we can apply this. You use it to actually find some derivatives. So when I'm looking at this thing, the first thing I think to do is the obvious. Put 1 in for x and see what happens. Well, if I do that, I get the log of 1 divided by 1 minus 1, which is 0 over 0, and that is one of our indeterminate forms. Right? This is a situation where L'Hopital's rule applies. So what L'Hopital's rule says is I'm just going to take the derivative of the top and the derivative of the bottom and reevaluate. Right, so if I do that, this becomes the limit x approaches 1. The derivative of the log of x is 1 over x. The derivative of x minus 1 is 1. Now I'm going to put 1 in again. This is 1 divided by 1 over 1, which is 1, and that's it. We're done. Right? I love L'Hopital's rules. One of the neatest little tricks that we have that we're going to put in our toolbox through this entire class. Right? Let's just do these indeterminate form limits really, really quickly. Okay, so why don't you give this one a try? Right? Try this out, see what you come up with. Okay, right. Step number 1 is our verification step. If I try to take the limit, the limit of the log of x as x goes to infinity is infinity. The limit of the square root of x as x goes to infinity is infinity. Yes, this is an indeterminate form. Excellent. Let's apply the rule. Right. First, the limit stays the way it was. The limit as x approaches infinity. The derivative of the log of x is 1 over x. The derivative of the square root of x, remember, think of this as x to the 1/2. Right, so this is 1/2 x to the negative 1/2. Okay, which didn't immediately clear things up. Actually, if we try to just put infinity in there again, we get 0 over 0 again. Okay, that was a little awkward, but let's just clean it up first. Let's do a little algebra, simplify this messy expression in here. This is the limit as x approaches infinity of 1 over x over 1 over 2 x to the 1/2. I just kind of move the negative exponent down to the denominator. And now let's do what we do to simplify fractions. This is the limit x approaches infinity, 1 over x times 2 x to the 1/2 over 1. And we can kind of ignore the 2, bring the 2 out in front. 2 times the limit x approaches infinity, and subtract the exponents. Right? This is x to the negative 1/2. All right, so this is 2 times the limit x approaches infinity, 1 over x to the 1/2, and that limit is 0. So this is 2 times 0, which is 0, and that's it. There's our answer. Right? There's the limit. Okay, so how about this thing? Maybe not immediately obvious that this is an indeterminate form, that this is a L'Hopital's rule situation, because they don't have a fraction, just to begin with. Right? Indeterminate forms require fractions. But look, here's what I'm going to do. Let's clean up that negative exponent. Let's make this the limit x approaches infinity, x to the 3rd, over e to the x. Okay, good. Now, if I try to take the limit of the numerator and denominator, the numerator goes to infinity, the denominator goes to infinity, and yes, now this is a L'Hopital's rule situation. All right, so let's differentiate. This is the limit x approaches infinity. Derivative of x cubed is 3x squared. The derivative of e to the x is e to the x. And we still have a problem. This is still infinity over infinity. Right? That actually didn't clean it up, but that's okay. Look, it's infinity over infinity. It's a L'Hopital's rule situation again. So apply the rule again. Right? I'm going to differentiate a second time. This becomes the limit x approaches infinity, 6x over e to the x. And hopefully you see the trend, right? You see where this is going to end up? That's still infinity over infinity, but if I do it one more time, this becomes the limit x approaches infinity of 6 over e to the x. And now I get my answer. Right? The top is staying constant. The bottom is going to infinity. It's blowing up. It's getting huge. So this limit is 0. And there you go. We got our answer. Right? Sometimes you got to do it more than once. Right? That's okay. I kind of had to whittle away at that numerator, right? Until I finally got rid of all of the x's, and then I was able to get the final conclusion. So take a look at this one, right? Try working this out on your own, right? Pause the presentation, then come back and we'll go over it together. Okay, so again, this is a situation where it's not immediately obvious that lHospital's rule applies because there's no fraction. But just like where I was able to, where I saw that negative exponent and said, well, okay, negative exponent is kind of another way to write a fraction. I'm looking at this and I see that cotangent of x. I'm thinking, okay, cotangent of x is really a fraction, right? This is, I'm going to rewrite it, the limit x approaches 0, x cosine of x over the sine of x. Right now, this is the lHospital's rule situation. If you put 0 in, the numerator becomes 0 times 1, which is 0, and the denominator is just 0. Good. So we're going to apply the rule. It's going to be maybe a little more complicated, but just because we have a product rule situation going on in the numerator. So the numerator, let's see, this will be the limit x approaches 0, the derivative of x times the cosine of x, plus x times the derivative of the cosine of x, just working out the product rule there, over the derivative of the sine of x. Okay, that's the easy one. That's just the cosine of x. All right, so let's see. Now we have the limit x approaches 0. Derivative of x is 1, so that's cosine of x minus x sine of x over the cosine of x. Now, let's try putting 0 in and see what happens. This becomes the cosine of 0 minus 0 times the sine of 0 over the cosine of 0. Well, the cosine of 0 is 1. Sine of 0 is 0, but 0 times 0, that's 0. Cosine of 0 is 1, and there's my answer. Right? This limit is 1. Okay, so those are kind of some standard issue lHospital's rule situations. There are one or two others, right? One or two other situations that may not that are kind of like the last two. They may not immediately scream that this rule applies, but if we work with them a little bit, right, we can turn them into an indeterminate form and then apply our new rule.